SwayamPrabha. Digital India. Educated India.
Good morning. This is the fifth lecture on steam turbine. Here I'll solve a problem illustrating the underlying principle of flow through nozzle. Hope the problem would be helpful to you. I have solved here a problem on nozzle. The statement of the problem is the gases expand in a propulsion nozzle from 3.5 bar and 425 degrees Celsius to a back pressure of 1 bar at the rate of 18 kg per second, taking the coefficient of discharge of 0.99 and a nozzle efficiency of 0.94. Calculate the required throat and exit area of the nozzle. Neglect inlet velocity. Take gamma is equal to 1.33 and Cp is equal to 1.113 kilojoule per kg per K for the gas. Let me solve the problem. Now, what are the quantities are given? Just let me put that in one side. Now, please note that P1 here, static pressure at inlet, is 3.5 bar. T1 is 425 degrees Celsius. That's equal to 698 Kelvin. P2, pressure at exit of the nozzle is 1 bar. M dot mass flow rate through the nozzle is given as 18 kg per second. Coefficient of discharge CD is given as 0.99. Nozzle efficiency eta N is 0.94. You need to calculate throat area AT and exit area of the nozzle A2. Thus, I'll show you how to calculate throat area and exit area of the nozzle. Now let me draw a schematic of the nozzle that will help you to visualize. So this is our nozzle and this is inlet area or inlet section 1, and this is the exit section 2. This is the throat T. So E1 flow is entering at inlet, leaving at exit. E1 be the cross-section area at inlet. A2 be the cross-section area at exit. Similarly, AT be the cross-section area at the throat. Furthermore, giving gamma of the gas as 1.33 and Cp as 1.113 kilojoule per kg per K. Right. So I can evaluate our characteristics gas constant as Cp minus Cv. That can be written as Cp into gamma minus 1 by gamma. You know the value of Cp, you know the value of gamma. If you evaluate that, you will get 0.276 kilojoule per kg per K. Okay. Now I can use the gas equation, that is P1 V1 is equal to RC into T1. From here I can calculate V1 specific volume at inlet, which is RC T1 by P1, and I have calculated R as 276. Temperature at inlet T1 is 698 Kelvin, 698, and P1 is 3.5 bar, so 3.5 into 10 to the power 5. This is Pascals. I have converted to bar in Pascals. So if you calculate this, you will get 0.55 meter cube per kg. So you have evaluated specific volume at inlet. Now if I neglect the approach velocity, so that is, if I neglect, it is given. If I neglect that inlet velocity, that is V1, then what I'll get? I'll get eta n, that is nozzle efficiency, is equal to V2 by V2 isentropic exit velocity whole to the power square, where V2 be the actual exit velocity at the section 2 and V2 isentropic be the isentropic exit velocity. So thus V2, I can get actual velocity at the exit of the nozzle is equal to V2 isentropic into root over eta n, nozzle efficiency. Now I have derived this expression, that is V2 isentropic is equal to root over twice gamma by gamma minus 1 P1 V1 within bracket 1 minus P2 by P1 to the power gamma minus 1 by gamma. Then I can evaluate actual exit velocity V2. V2 can be written as root over twice gamma by gamma minus 1 into P1 V1 to the power 1 minus P2 by P1 to the power gamma by gamma minus 1, gamma minus 1 by gamma into eta n, nozzle efficiency. This will be the actual velocity. I know all the values. If you put all the values, you will get. I'll show here in detail. That is 2, 1.33 divided by 0.33 into P1 means 3.5 into 10 to the power 5. What is the value of B1 into 0.55 within the bracket 1 minus P2 is 1 bar, 1.0 divided by 3.0, 3.5 to the power 0.33 divided by 1.33 into nozzle efficiency is 0.94. Now if you calculate, you will get actual velocity is 624.24 meter per second. Thus, I have evaluated actual velocity, right? Now, I'll show you I can calculate actual velocity is another way from fundamentals using the definition of nozzle efficiency. So how? Let me draw here TS diagram indicating the flow through the nozzle. This is the inlet pressure P1. This is the exit pressure P2. This is temperature and entropy diagram illustrating flow through the nozzle. So 1, 2 dash with the isentropic expansion to the nozzle, and 1, 2 with the actual expansion to the nozzle. Then I can write the nozzle efficiency eta n is equal to H1 minus H2 divided by H1 minus H2 dash. That means actual enthalpy drop divided by isentropic enthalpy drop within the nozzle. That can be if I consider within the temperature range Cp remains constant, then I can say T1 minus T2 actual temperature drop divided by isentropic temperature drop, that is T1 minus T2 dash. This is our T1 and this is our T2 dash, 1 and 2 dash, and this is our actual temperature T2. Now from here I can evaluate actual temperature. I'll show you the whole way. Now I can write T1 by T2 dash, that is isentropic temperature ratio, can be stated as with respect to pressure ratio using isentropic relation gamma minus 1 by gamma, right? Now here I know P1, I know P2, and thus I know the value of gamma, so I can evaluate T2 dash. So I have evaluated, if you do the calculations, I'm not showing in detail, that I have calculated T2 dash as 1.5 Kelvin, right? And now, using the definition of efficiency, I can write 0 from the definition of efficiency now. I can write 0.94 is equal to 698 inlet temperature minus T2 actual temperature at exit divided by 698 inlet temperature minus isentropic temperature T2 dash. Thus from here I can project T2. If you calculate T2, you will get T2 is equal to 522.7 Kelvin. So I have got actual temperature of gas at exit. Right. Now we have V2 actual velocity at exit is equal to root over twice H1 minus H2 if I neglect approach velocity. So that can be written as root over twice Cp into T1 minus T2. I know the value of T1, I know the value of T2, I know C. So if you calculate, put all the values, and if you calculate, you will get V2 is equal to 624.6 meter per second. So look, I have evaluated V2 following another route using fundamentals from definition of nozzle efficiency. Previously, I got the value V2 as 624.24. Now I got the value of 624.6 meter per second. Now I can easily evaluate that exit area A2 of the nozzle. Let's go to the next page. So I can use the equation of gas to calculate specific velocity at the exit. So then P2V2 is equal to R into T2. Thus from this relation I can get small v2 is equal to R T2 divided by P2. I know the value of R, that is 276. Values of T2 that I have got is 522.7, and P2 is 1 bar, that is 1.0 into 10 to the power 5 pascals. Then I got the values of V2 as 1.443 meter cube per kg. So I have calculated a specific volume at exit of the nozzle. Hence, from continuity equation, what I'll get? M dot mass flow rate into specific volume at 2 is equal to A2 area of the nozzle at exit into V2 velocity of the nozzle at the exit. Thus A2 Thus A2 is equal to m dot V2 divided by capital V2. Capital V2 being the velocity. M dot is given as 18 kg per second into small v2. I have calculated 1.443. Capital V2 I have calculated 624.24 meter cube per second. So if I do that, I'll get A2 exit area is coming 0.0416 meter square. Thus I have got an answer that exit area of the nozzle. Now I'll go to the second part, evaluating area of the throat of the nozzle. So I'll solve now part 2, that is throat area AT. Now here to evaluate throat area, I have considered the losses occur in the divergent part only. Hence, I have neglected the loss that's occurring in the convergent part. Let us also consider that P T star be the throat pressure. Throat pressure. This is when I am putting something is star that represents the critical condition. Hope do you remember that. So PT star is the throat pressure at critical conditions. I know the relation that PT star divided by P1 is equal to twice divided by gamma plus 1 to the power gamma by gamma minus 1. I know the value of gamma, so I can evaluate the ratio here. This ratio is coming as 0.5404. So thus I can evaluate PT star as I know the value of P1. So PT star will be here 1.89 bar. Now please note that I have written since P2 is less than PT star, definitely the throat is choked or the nozzle will be choked. So P2 was 1 bar, PT star I have calculated as 1.89 bar. Since the exit pressure is less than the critical pressure, definitely the nozzle is choked. So discharge to the nozzle is maximum. Now, since I have considered the loss in the convergent part is 0, So I can write now PT by P1. The ratio can be given by some isentropic equation, which is gamma minus 1 by gamma is equal to TT, temperature at throat. TT means temperature at throat, divided by T1. This is because of the fact that I have neglected the losses in the convergent part. Thus, I can consider that in the convergent part, the flow would obey the isentropic relations. Hence, I can evaluate from here. Now I have calculated PT star. This can be put as star. I have evaluated PT star. I know the value of P1. I know gamma. I know T1. So everything is known. So I can evaluate TT, that is temperature at the throat, which is coming as 599.15 Kelvin. So I have evaluated temperature at throat. You are requested to check all the calculations. Now I can evaluate Vt, that is velocity at throat, which is equal to root over twice Cp into T1 minus Tt. Tt being temperature at the throat, which I have evaluated. This is equal to root over twice into Cp, that is 1113. Value of T1 is 698 and Tt has been calculated as 599.15. If you calculate, you will get Vt as 469 meter per second. Now, from the definition of coefficients of discharge CD, CD is nothing but m dot actual discharge divided by isentropic discharge m dot is. So from here, I can evaluate m dot is as m dot divided by CD. M dot is given by 18, CD is 0.99. So if you calculate, you will get 18.18 kg per second. Please note that I'll have to evaluate m dot isentropic to correlate with Vt, because within the convergent nozzle I am considering the flow become isentropic. So hence I can write from continuity m dot is into Vt, specific volume at the throat, is equal to area of the throat, At, into Vt. Now, I have not yet evaluated the specific volume at the throat. Specific volume at the throat, Vt, I can get R T by P at the throat. Everything. I know temperature at the throat, I know pressure at the throat, so I can get Vt. Okay, if you calculate this VT now, you get 0.875 meter cube per kg. So you can evaluate AT. AT is nothing but m dot isentropic into specific volume, which I have calculated here, right? Divided by VT. So m dot isentropic is 18.18. VT specific volume is 0.875. VT velocity at the throat is 469. If you evaluate, you'll get area of the throat as 0.034 meter square. Thus, I have calculated area of the throat as 0.034 meters square. Hence, I have solved the problem calculating area, exit area of the nozzle and area of the throat. I request you to solve similar problem and thank you for listening.